Hello viewers, welcome to another series of the Automotive Technology tutorials brought to you by the Automotive Technology Institute. In this series, we are going to cover the automotive air conditioning system. Under the automotive air conditioning system, we are going to have a number of tutorials. The first one that we are going to cover will be principles governing air conditioning systems. Then we shall look at the basic air conditioning system cycle. Then we shall look at a detailed discussion of the individual components of the air conditioning systems, and under this we're going to look at the compressor, we will look at the thermal expansion valve, and finally we will look at the condenser and the evaporator. So to start off, there is an image here we can see. It has two containers here. The two containers contain a liquid, and the liquid is under a certain temperature and pressure, both the first and the second container. The temperature of the first one is obviously lower than the temperature in the second one. Reason being, the second one has a burner to it which has raised its temperature. We can also see that the containers are connected to a pressure gauge, and we can see the reading on the pressure gauge that is connected to the first container is lower than the pressure gauge that is connected to the second container. So this is one of the principles that we shall be learning in the course of this tutorial, that temperature is directly proportional to pressure, holding other factors including volume constant. Consider in this case, we have the temperature of the first container being lower than the temperature of the second container. Consequently, the pressure of the first container will be lower than the pressure of the second container, considering the two have the same volume. So let's jump into the objectives of this tutorial. One, we will have to define heat and heat transfer. We'll identify the principles of heat and heat transfer. We will revisit the various states of matter. And finally, we will identify the principles that govern air conditioning systems. Just as an introduction, it is good to note that in as much as we are looking at the automotive air conditioning systems, the principles that are applied in the automotive air conditioning systems are similar to those applied in any other air conditioning system, even in refrigeration systems. We understand that air conditioning is a key thing, especially when we are in extreme weathers like in deserts and in places that experience winter and summer seasons. And even in the tropical areas, we find that in most cases the temperatures are always high on the outside. Therefore, we need the vehicles, because anytime that you leave your vehicle in both extreme temperatures, whether cold or hot, you will come back and find that the cabin of the vehicle is very, very hot. So what the air conditioning system does is it controls the climate of the vehicle cabin so that you can be able to maintain it within a comfortable temperature. So we dive into the definitions of heat and heat transfer. Starting off with heat, heat is defined simply or basically as molecules in motion. I know this is a contradiction of what we have known as human beings as what is referred to as heat, because what we refer to as a hot surface is that which feels hot to our touch. On the contrary, we find that any body that has a temperature above negative 273.15 degrees centigrade or 0 Kelvin, that body has some heat. It is because at this temperature, that is at 0 Kelvin, the molecules are not, they are not in motion. That is, motion stops at this temperature. But above this temperature, there is motion. And whenever we have motion of molecules, we consider that there is heat in that body. Therefore, any body that has a temperature that is above 0 Kelvin, that body has heat. So if you have an ice cube that is at negative 100 degrees centigrade and another that has negative 200 degrees centigrade, the two bodies contain heat. However, the body that has negative 100 degrees centigrade has more heat than the one that is at negative 200 degrees centigrade. When we put these two ice cubes next to each other or close to each other, we will realize that after some time they will attain a common temperature of about negative 150 degrees centigrade. The process through which these two bodies attain the same temperature is what is referred to as heat transfer, because heat moves from the body that is at negative 200 degrees centigrade to the body that is at 100 degrees centigrade, so that the two bodies now attain the same temperature. Hi, we first look at the first principle of heat and heat transfer. Heat is a form of energy, and we all know the law of conservation of energy that states that energy can neither be created nor destroyed. It can only be changed from one form to another. Heat also maintains this law, or it obeys this law of conservation of energy. Temperature is a measure of the amount of heat energy in a particular body. So when we talk of a body at negative 100 degrees centigrade, what we are basically saying is that body has a certain measure of heat energy, which is equivalent to negative 200 degrees centigrade. Therefore, temperature, it is basically a measure of heat energy in a particular body. So as a result of the law of conservation of energy, to increase the temperature of a body, energy has to be added to it. Similarly, to reduce the temperature of a body, heat has to be removed from it. So if you keep an ice cube in a place where it is completely isolated from the environment, from anything, such that it has only the heat that it is contained, that ice cube will remain at that temperature, because for it to increase its temperature, for it to decrease its temperature, it has to have an external source of energy, because it cannot create its own heat. Therefore, for it to increase, it has to have an external source of heat. For it to decrease in temperature, it has to have an external extractor of heat. And an external extractor can be anything. It can be a body that is lower, of lower temperature than itself. It can be anything. It can be anything. So we look at the second principle of heat transfer. Heat is transferred from the body with more heat to the body with less heat. For instance, here we have two bodies. One is at 100 degrees Fahrenheit and another is at 75 degrees Fahrenheit. What will happen is heat will flow from the body at 100 degrees Fahrenheit to the body that is at 75 degrees Fahrenheit until the two bodies attain equilibrium. That is when heat transfer will stop. The rate of heat transfer is dependent on the temperature of the two bodies. So if we have a body that is at negative 200 degrees Fahrenheit and another that is at negative 350 degrees Fahrenheit, we realize that in this case, the difference in heat is negative, or is 150 degrees Fahrenheit. In our first case here, the difference in temperature was 25 degrees Fahrenheit. Therefore, the rate of transfer of heat of these two bodies will be higher than the rate of heat transfer in these two bodies. Why? Because the difference in temperature of this first one is lower than the difference in temperature of this second one, regardless of the fact that this looks like it is at a lower, or rather the temperatures are low. The rate is a factor of what is the difference in the temperature of the two bodies. So the heat transfer increases as the difference in temperature between the two bodies increase. That's basically what we have just discussed. So the third principle of heat and heat transfer: the mass of an object is not affected by a change in temperature. However, the pressure that particular mass exerts on the surrounding increases as temperature increases. This will be observed when looking at the different states of matter. So once we move into the different states of matter, we'll be able to note this third principle of heat and heat transfer, that the mass of an object, when it is subjected to a change in temperature, it doesn't change. But when you subject the same mass to a change in temperature, then the pressure that that particular body exerts on the surrounding. May it be the container it is placed, or rather it is contained in, or the surface it's placed in case of an ice cube, or the container it is contained in case of a vapor, because in that case we will have to say cork so that the vapors do not evaporate. That volume will change and the pressure will change. Matter and the states of matter. So matter is anything that occupies space and has weight, and it exists in 3 states. This is something that we have seen and heard over the years, that it exists in either solid, water, or liquid and vapor. So if we take an example of water, the 3 different states of matter of water are ice, which is here. Now this is a block, that is why it's a solid. That's a block. Then in liquid form, it's basically what we refer to as water, but it's just but one of the states of water. Then finally we have the gas state or the vapor state of water, which is what is referred to as steam. So the state of water is determined by the amount of heat that the water contains. With less heat, it will be in solid state. If you increase that heat, then we expect that it will change from solid into a liquid. If you increase that further, the liquid will now change its state to vapor. As mentioned earlier, we said that as states change from one state to the other, the pressure that that particular state or that particular mass exerts on the surrounding increases. So the arrows that we have here, they are literal indications of the amount of pressure that this mass of water is exerting. So we can see that for these ones, they are just a few and exerting just in one direction. These ones, when it's in liquid form, the pressure increases and it's now both downwards and outwards or sideways. Then when it's in vapor, it's just all over. So it's exerting pressure both down, sideways, and okay, let's look at what happens for matter to change from one state to the other. When we are looking at changes in state of matter, there are 2 factors that come into play: the molecular bond and the molecular kinetic energy. The molecular kinetic energy is a factor of the amount of heat energy that is contained in that substance. The molecular bond is a factor of the substance itself, like the molecules of that substance, what is their molecular bond. So that is determined by the substance itself, while the kinetic energy is determined by the amount of heat or the temperature of the body in simple terms. So we realize that different substances exist in different states. This is basically because at room temperature, the kinetic energy of the molecules is more or less the same because these substances are being subjected to the same amount of heat energy at room temperature. What varies is the molecular bonds of these substances. For instance, we know that there are substances that exist as solids, others exist as liquids, and others exist as a gas or as vapors. The difference is that the substances that exist as a solid, their molecular bond is way higher than the kinetic energy at room temperature of the molecules. This enables the molecular bonds to be able to hold the molecules together and close enough together such that the substance remains as a solid. On the other hand, for those substances that exist as a liquid, the molecular bond is still higher than the kinetic energy, but not as high as for those that exist in solid. And for those that exist in liquid, we realize that the kinetic energy is now a little relatively high, enough to break some of the molecular bonds, and these breaks free the molecules such that they can be able to move to some extent, but not free to move like what we see in gas state. Therefore, in liquid state, the molecular bond is higher, but the kinetic energy is still close enough to be able to break some of the molecular bonds. In the gas state, or the substances that exist as a gas, the kinetic energy of the molecules is way high than the molecular bonds of the molecules. As such, the kinetic energy at room temperature is able to break the molecular bonds, and the molecules become free to move, and that is why that substance exists as a gas. Now, let's use our example that we have been using, that is water. We know very well that water exists as a liquid, and this is what we have. It is a liquid and it is in this state. Now, if we want to change this water, which is in liquid state at room temperature, into a solid, or into the solid state, we will have to extract heat from the water to reduce the kinetic energy so that it allows the molecular bonds to be higher than the kinetic energy, enough to be able to hold the molecules together. As such, now the water becomes a solid. On the other hand, if we want to change the water into as a vapor, which is steam in our case, we will have to raise or increase the heat energy so that the kinetic energy of the molecules becomes high enough to break the molecular bonds and free the molecules, so that the molecules now are able to be free. In such a state, we can actually say that the molecular bonds become insignificant to as compared to the kinetic energy. So that is basically what happens during the states of the changes in states of matter. It is just a matter of what is the amount of kinetic energy in the molecules as compared to the molecular bond of that particular substance. Sensible heat and latent heat are the two forms of heat that we are going to encounter when we are dealing with air conditioning systems. It is therefore important if we can be able to understand their difference and what they cause. The basic difference is that sensible heat causes a change in temperature and latent heat causes a change in the state of the body. It's also worth noting that changes in the amount of sensible heat can be recorded by a thermometer, while the changes in the amount of latent heat cannot be captured by a thermometer. So far, we have been able to define the main terms that we are going to come across when we are working with the air conditioning systems. So we are now in a position to look at the principles that govern the air conditioning systems. We well know that this is the main objective of this tutorial. So we'll just go right into it, and we're going to start with the first one, which states that an increase in pressure leads to an increase in temperature. This mainly concerns a substance that is enclosed within something, and the opposite is true as well, that if you decrease the pressure, then you're going to decrease the temperature as well. The second one is that a decrease in pressure leads to a decrease in the boiling point of a substance. Similarly, an increase in pressure will lead to an increase in the boiling point of the substance. Then finally, or the third principle, is that for a substance to change from one state to another, huge amount of energy is either absorbed or emitted. So these are the principles that form the backbone of the air conditioning systems. Any air conditioning system or any refrigeration system works on the basis of these three principles. So you don't really or necessarily have to memorize these principles because it's really not necessary. But for us to be able to understand these principles, we are going to carry out an experiment that will help us be able to look deeper into these principles and help us understand each of them. And once we are done with our experiment, we will have been able to understand the principles and we will be done with this tutorial. So in this experiment, we are going to have these apparatus. We will have a burner, we'll have the stand, a stool there, a round bottomed flask that will have water filled to about 3/4 way. Then we have a thermometer and a glass tube. The round bottomed flask will also have a rubber cork that seals the inside of the round bottomed flask from the atmosphere. Then the glass tube will also have a stopcock that is able to seal or to separate the inside of the round bottomed flask from the atmosphere. So you will be required to set up the apparatus as shown in this diagram. So in this experiment, we are going to carry it out in 3 different parts. The first part is going to demonstrate that principle that we have just listed. Then the other 2 parts are going to demonstrate the first and the second principle. So to start the experiment, you will need to have a stopwatch because you will be required to take some time readings. So to start off the experiment, just light the burner and let it heat the water in the round bottomed flask. As it heats, you realize that the temperature of the water will start rising from room temperature all the way up to the boiling temperature, which is at 100 degrees Celsius. What you will be required to do is to record the time it takes for the water temperature to rise from room temperature all the way to the boiling temperature, the time that it takes for that temperature change to occur. So when it starts to boil, release the vapors by opening the stopcock, and at this point record the level of the water in the flask or its weight. So allow the water to continue boiling to up to 4 times the time it took to raise its temperature from room to boiling temperature. And while the water is boiling, monitor the temperature reading. So observations from the first part of the experiment. At the start of the experiment, adding heat increased the temperature of the water. So if you can remember when we were defining the different forms of heat that we have, we say that we have that form of heat that is called sensible heat. This is heat which when added, it increases the temperature of the water. So this is what we are talking about. As the water was boiling, no temperature change was recorded. This is what we call the latent heat, because at this time we don't expect any increase or any thermometric reading being recorded, any changes in thermometric reading being recorded at this time, because the heat that is now being added to the water is causing a change in state, which is from liquid to vapor. After boiling for the required time, the water level in the flask went down by about half. So of course we expect that the water in the flask would reduce because we are evaporating the water. So some of the water will change state from liquid to vapor. So what changed into vapor, according to the observation at the end of the experiment, is about half. Half of that, the water changed from liquid state into vapor state. So explanation to the observations from the first part of the experiment. At the start of the experiment, we could not see a change in temperature because the heat that was being added into the system is what is known as sensible heat. We have just listed that, or we have just said that. After the water attained boiling point, we could not record any temperature change because the heat being added was now latent heat. That's not new as well. It took 4 times longer to change half the amount of water from liquid to vapor as compared to raising the temperature of the water. Now this is where the tire meets the road, because the principle that we are discussing in this first part of the experiment is on the amount of heat that is absorbed when we are changing the state from one the state of matter from one state to another. So we noted that during the experiment, we heated the water. After reaching the boiling point, we heated the water 4 times longer than it took to raise the water from the room temperature to the boiling temperature. And during this time, only half the amount of water turned into vapor. This means, in simple terms, that the amount of energy that was used to evaporate half the amount of water in that flask is equivalent to 4 times the amount of energy that was used to raise the temperature of the water from room temperature to the boiling temperature. Why is it that the amount of heat that is consumed during a change of state is so high compared to that is consumed when we are changing the temperature? It is basically because of what we were discussing when we were discussing what happens during the changes in state. When we are changing the temperature, or when we are raising the temperature of water from room temperature to the boiling temperature, what we are doing is we are only increasing the motion of the molecules, which consequently increases the temperature of the molecules. But when we are talking about state change, here we are supplying enough energy to overcome the molecular bonds. So we have to supply the molecules with much more heat, much more energy, so that they gain the required kinetic energy so that they can be able to now overcome the molecular bonds that are holding them together, and they break free for them now to be able to change the state from liquid into vapor. And that energy is quite a lot. That is why a lot of energy is required during the change in state. Now, let's go into the figures. I believe this will make more sense to a majority of us. Assuming we have 1 kg of water in that jar, and considering that energy is measured in joules, the quantity of heat required to raise 1 kilogram of water by 1 degree centigrade is 4,186 joules. This is something that has been proved scientifically. So this is just something that we are extracting from other experiments. So the same mass of water, that is the same 1 kilogram of water at 100 degrees centigrade, has to absorb 2.26 megajoules of heat energy to change from a liquid at 100 degrees centigrade to a vapor at 100 degrees centigrade. Just to make sure that we are on the same page on this, can we be able to figure out the difference that we have here? The amount of energy that is required to evaporate the same mass of water, and the amount of heat that is required to raise the temperature. Assume that we have 1 kilogram of water at 0 degrees centigrade. If we are at 0 degrees centigrade, therefore we will have to move over 100 degrees centigrade. So the amount of heat that we shall consume here to change the water from 0 degrees centigrade to 100 degrees centigrade is equals to 100 multiplied by 46, 4186 joules, which gives us about 418,600 joules. Now, this is the amount of energy that is consumed when raising the temperature of the water from 1 degrees to 100 degrees centigrade. Now, compare that to the amount of energy that is consumed when we are evaporating the same amount of water and changing it from liquid to vapor. This is about 5 times this. That is what we are talking about. When we are evaporating, when we are changing state, quite a huge amount of water, of energy is required. Let's go back to our experiment. Now, assuming that the room temperature was at 25 degrees centigrade, and we raised the water from room temperature to the boiling temperature, which we also assume is at 100 degrees centigrade. Therefore, we raised the water through 75 degrees centigrade. Therefore, to obtain the amount of energy that was consumed in this process, that is the process of raising the water temperature from room temperature to the boiling temperature, we take the 75 degrees centigrade multiplied by 4,186 to get 313,950 joules. Now, this is the energy that was used to raise the temperature from 25 to 75 degrees. So we went further into the experiment and we took the time that we had recorded that the water took to increase the temperature from room temperature to boiling temperature. We multiply that time by 4 and now boiled the water for that amount of time. Basically, what we were doing is that we were supplying 4 times the amount of energy that we supplied when we were raising the temperature of the water over 75 degrees, and this is what we have. So we have 313 joules, 313,950 joules multiplied by 4 gives us this amount of energy. So this is the amount of energy that was consumed during boiling. So if 1,255,800 joules is just over half the amount required to vaporize the whole mass of water, then we can conclude that this is why only half the water vaporized even after heating for 4 times longer, because during this time the amount of energy supplied is just over half what is required. So this now leads us to the first principle of matter that forms the basis of air conditioning systems, that
large quantities of heat are required to change matter from one state to another as compared to raising the temperature of the same mass of water. That is basically what we have been explaining or demonstrating in that first part of the experiment. So let's remember this, that large quantities of heat are required to change matter from one state to another as compared to raising the temperature of the same mass of matter. So here we have a graphical representation of the first principle of matter, and this graph shows the stages that our example, which has been water, goes through from a solid state all the way to a vapor state. So it is starting off with a solid at negative 100 degrees centigrade. This is ice, an ice block at negative 100 degrees centigrade. Once heat energy is added to this block of ice, it gains heat up to 0 degrees Celsius. So the heat that is gained here is sensible heat because it raises the temperature of the ice block from negative 100 degrees centigrade to 0 degrees Celsius. Now the amount of heat energy that is consumed in this process is about 200 kilojoules. So at 100 degrees, at 0 degrees Celsius, if we add now more heat energy, what we are going to do is we are going to have the ice block melted. And during this melting, the heat that is absorbed is what is known as latent heat of fusion, and it is equivalent to about 334 kilojoules. So we continue to supply more energy to this mass of 1 kilogram of water now, and we raise it through 100 degrees Celsius, from 0 to 100 degrees Celsius. And here, this is now sensible heat because it's actually raising the temperature of the water. And the amount of energy that is consumed here, as we have already seen, is about 418 kilojoules. We are now at 100 degrees Celsius, and the water is ready to vaporize. So adding more heat, we are going to vaporize this substance, and the heat now that is being added is what is known as the latent heat of vaporization. And we can see that it's a huge amount of energy from here all the way to here, a very huge amount of energy, and we have already seen it's equivalent to 2.2 megajoules of energy. So we are now at a complete vapor, or the water has already turned completely to vapor, and now if we add more energy, we are going to superheat that vapor. And to superheat over just 100 degrees Celsius, that is from 100 degrees Celsius to 200 degrees Celsius, we are only consuming about 200 kilojoules. This shows you how small of energy is required to raise temperature as compared to the amount that was used when changing the state of matter. Let's look at some terms associated with changing state from liquid to vapor as used in the air conditioning systems. First, we're going to start with saturation. And we find that when a substance exists in both liquid and vapor states at the same time, it is said to be at saturation. At this point, adding heat changes state to vapor and extracting heat changes state to liquid. Next, we are going to look at superheat. Superheat is the heat added to a substance after it has completely changed state into vapor. This heat increases the temperature reading of the vapor. Superheat is given by the temperature reading minus the saturation temperature. Finally, we have subcool. This is the heat extracted from a substance after it has completely changed state into liquid. It decreases the temperature reading of the liquid. Subcool is given by the saturation temperature minus the temperature reading. Now, let's go back to the graphical representation of the first principle of matter and see how the terms that we have just defined come into play in regards to the air conditioning system. So at the atmospheric pressure, the saturation temperature of water is 100 degrees centigrade. This is the saturation temperature, and this is why you can see that the change in state from water to steam is occurring at this temperature because that is its saturation temperature. Now, the saturation, or rather what we are calling a saturated substance for water, between this point and this point, the water is said to be at saturation. Why? Because after this point, the water has already achieved the boiling temperature, and any more heat that is added into it, doesn't matter at what point it is just causing evaporation to start. So just after that, we start to see vapor being formed, and all the way we have both water and steam, or water and or liquid and vapor in this substance. So at this point and at this point, these two sections are the areas over which saturation, or our substance, which is water, is referred to as saturated. Now let's move on to the next one, which is superheat. So we say that superheat is the heat that is added to a substance after it has changed into vapor. So at this point now, the water has already turned into vapor fully at this point. So all the liquid has changed into vapor. So adding any more heat will cause the temperature now to rise from the saturation temperature of 100 going up. Say we add to a point where the thermometric reading gets to 110 degrees centigrade. So to get the superheat value, we will take the thermometric reading, which is 110 degrees Celsius, then subtract the saturation temperature, which is 100 degrees Celsius, and we are going to get the superheat value as 10 degrees Celsius. So in the air conditioning systems, superheating occurs in the evaporator. Of course, we are going to find this, but I just want you to be able to link the dots, or just know this in advance that superheating occurs in the evaporator. And one of its importance is that it ensures that all the liquid or all the refrigerant has changed from a liquid state into a vapor state. You will realize that this is very important because after the evaporator, what you have is the compressor, and no liquid should go into the compressor, otherwise it will compromise the system. So the superheat is also, this superheat value is also used in controlling the air conditioning system, this value. So this is what the air conditioning system uses to know if it should increase or it should feed the system with more refrigerant, or what it should do. That is, this is what it uses to know what it should do in order to maintain the temperature that is desired in the room or in the vehicle cabin. So let's move on now to the subcool. So subcooling occurs after all the vapor has turned into a liquid, which is at this point. So at this point, we have all the vapors have turned into a liquid. Now, if we continue to extract heat from this substance, we'll realize that the thermometric reading will start to decline or to decrease, because now the heat that we are extracting, it is now not being used to change the state, but rather it's being used to as a sensible heat, and we will realize that the temperature will decrease. If the temperature decreases from 100 degrees, which is the saturation temperature, and the thermometric reading becomes 85 degrees Celsius, then the subcool value will be 15 degrees. So in the air conditioning systems, the subcooling is done in the condenser, and it ensures that all the vapors have turned into liquid, and this is for the sake of ensuring that the air conditioner is operating at an efficient level. So say that the subcool comes all the way up to here, and the superheat comes all the way up to here. Now, between this region, or this point, and this point, this is where air conditioning occurs. That is basically the cycle of air conditioning. So we have on this end the condenser. It changes the liquid into a subcooled liquid. Then on the other end, the evaporator ensures that all the liquid has turned into a vapor, and it goes backward and forward, backward and forward. That is where the refrigeration system occurs. Let me preempt something here, and I know it's just to help you understand the air conditioning system later. Now, at the saturation temperature, or at the saturation region, which is this one all the way, this is the saturation region. How the air conditioner is able to efficiently and very fast cool the air in the vehicle cabin is it ensures that at this saturation temperature, the saturated substance, or the saturated liquid, it is hungry for heat. by by ensuring that all the conditions that should be there for the substance or for the liquid to be a vapor, they are provided, except heat. So this saturated liquid will be hungry for heat. Therefore, if air at any higher temperature than the temperature of the refrigerant, or the the boiling point of the refrigerant passes over the refrigerant, it will definitely be absorbed into it will be absorbed by the refrigerant. And we know that the fact that a lot of it is required to change the refrigerant from a liquid into a vapor, it ensures that the air conditioner can always be able to absorb heat from the air cabin. That is basically what the air conditioner does. And I believe by the time we will be coming to understand the cycle or to discuss the cycles of the air conditioning system, we will be able to remember this, and it will be easy for us to understand that cycle at that point.
Just before we move into the second part of the experiment, let's try and connect the dots so that we can see how far we have come. So we have already listed the three principles that we are going to cover in this tutorial. And we say that the first principle was that the pressure of a substance is directly proportional to its temperature. The boiling point of a substance is directly proportional to its pressure, and that the amount of heat that is absorbed or released during a state change is very, very high. So far, or rather in the first part of the experiment, we have focused on the third principle, which we can also state as the latent heat is very high as compared to the sensible heat. I'm sure now we already know what those terms stand for. So in the next two parts of the experiment, that is part 2 and part 3, we are going to look at the other two principles. That is, pressure is directly proportional to temperature, and that the boiling point of substance is directly proportional to its pressure. What you will realize that every experiment, part 2 and part 3, each of them, it illustrates the two at the same time. But part 1, or rather part 2, will be a reverse of part 3. And even the vice versa. It can be said that part 3 is a reverse of part 2. So what we are going to do in part 2, it will illustrate the two principles. And again, what we are going to do in part 3, it will also illustrate the two principles, but in a reverse way. So let's move on to part 2. So let's remember that our water is still boiling, and we have already evaporated half of the water. So to continue now with the experiment, initially we were boiling the water and we were letting the vapors to escape into the atmosphere. So now what we are going to do is that we are going to close the stopcock so that we can trap the vapors or the steam that has been formed inside our flask. What we are supposed to take note of is the thermometric reading. Note the changes that occur on the thermometer and record that. So observations from the second part of the experiment. On closing the stopcock and continually heating, the thermometric reading increased from 100 degrees centigrade to 110 degrees centigrade. That was very clear from the experiment. What exactly happens in this part of the experiment? When we close the stopcock and still continue heating, the vapors that are now being formed are trapped within our round bottomed flask. When we were discussing what happens for state of matter changes to occur, we realized that when we heat a substance, we increase the kinetic energy of the molecules. And what this does is it increases the molecular motion. Now, we also noted that we had to do a lot of heating. We had to heat for a long period of time for these state changes to occur. Therefore, a lot of heat was consumed. And with the increase in the amount of heat that is consumed, what it does is it consequently increases the molecular motion enormously. That the molecules are now bouncing all over because they have a lot of kinetic energy as a result of our heating. So what does this heating or this increase in molecular motion do? The increase in the molecular motion significantly increases the pressure the substance exerts on the container it is held in. So in our case, the increase in molecular motion is causing the molecules to bombard the flask at a very, very high rate. And this is what translates into pressure. And the high rate translates to a high amount of pressure. Let us note that this is the first principle, that we have increased the pressure, we have increased the temperature, and now the pressure has increased. That is the first principle. So, after the pressure has increased, what happens? We note that the boiling point of the water increases. And this is seen by the increase in the thermometric reading. Now, we very well know that this cannot be sensible heat, in as much as we know that it is sensible heat that causes an increase in the thermometric reading. This cannot be sensible heat because the water was already boiling. So the substance is already at saturation. So it can any increase in temperature or any increase in the amount of heat that we are supplying, it cannot change the temperature reading. It can only convert this substance from one form to the other because it's already at saturation. So what then causes this increase in the thermometric reading? It is the increase in pressure, which results to the increase in the boiling point. So that now, instead of the water boiling at 100 degrees Celsius, because of the increase in pressure, the water is now boiling at 110 degrees Celsius. This is now the second principle, where we said that the boiling point of a substance is directly proportional to its pressure. Note that in these two cases, our cork is closed. Therefore, the volume is constant. That is important to note, that while these factors will hold only if all other factors remain constant. So let's jump into the last part of the experiment, which is the third part. So we are supposed to arrange our apparatus as shown in this diagram, but note that we are not supposed to allow any pressures to be released to the atmosphere or the lowering of the temperature. Just the way we were in part 2 of the experiment, we are just turning the round bottom flask so that it can be as shown in this diagram. Then next, what we do is we pour cold water on the flask and observe the thermometric reading and of course record it. What do we observe in this part of the experiment? We observe that when we pour cold water on the flask, the thermometric reading dropped from the 110 degrees Celsius that it was reading in the previous part of the experiment to about 80 degrees Celsius. So what exactly happens in this part of the experiment? We have already noted that the third part, we can now say that the third part of the experiment is a reverse of the second part of the experiment. So even in explaining what happens in the third part of the experiment, it is just a reverse of what we found in the second part of the experiment. So while in the first part we were heating so that the water can form into steam and the steam gains a lot of energy. In this case, the steam loses its water to the cold. Sorry, the steam loses its heat energy to the cold water. The reduced amount of heat energy in the water vapor causes reduced water molecule motion. That means that now that this water, or rather this steam, which is water vapors, they are losing heat energy to the water that is being poured on the round bottom flask. Their motion will now start to reduce. Remember that this is exactly what we saw, or the opposite of what we saw in the second part of the experiment. Then with the reduced molecular motion, less pressure is exerted on the flask. So far, this is the first principle of matter that we are talking about, that a reduction in the temperature leads to a reduction in the pressure that substance exerts. Finally, the reduced pressure lowers the dew point of water and hence the reduction in the thermometric reading. So that is now the second principle, that a reduction in pressure leads to a reduction in the dew point. That is why we saw the temperature lowering from 110 degrees centigrade to 80 degrees centigrade. Normally it should be at 100 degrees centigrade, but it went way below 100 degrees centigrade to 80 degrees centigrade. So another form of the first principle of matter that forms the basis of air conditioning systems is what is normally known as the Gay-Lussac's law, which states that the pressure of a given mass of a gas varies directly with the absolute temperature of the gas when the volume is kept constant. We have already discussed this and we have seen that this is exactly what happens. So here is a graphical representation of the second principle of matter. So on the first scale, we can see that the temperature is at 1.5 atmospheres and the boiling point is at 112 degrees centigrade. On the second scale, the pressure is at 1 atmosphere and the boiling point is at 100 degrees Celsius. On the third scale, we can see that the pressure has now been lowered further to 0.76 atmospheres, and now the boiling point lowers to 92 degrees Celsius. Therefore, an increase in pressure increases the boiling point of water, and the vice versa is also true, that a decrease in pressure, which can be seen by this. Normally, at atmospheric pressure, which is 1 atmosphere, the boiling point is what is recorded as 100 degrees Celsius of water, which has been our sample substance from the start of this experiment. So if now we reduce the pressure from the atmospheric pressure to 0.76 atmospheres, the boiling point reduces to 96 degrees Celsius. And the opposite is also true, that when we increase the pressure from 1 atmosphere to 2 atmospheres, we realize that the pressure increases, or rather the boiling point increases to 112 degrees Celsius. If we draw a graph of temperature against pressure, then like we have seen in the previous case, that when we are increasing or lowering the temperature, we take the different readings of pressure. We take the different readings of pressure, and the values of temperature that coincide with the values of pressure. Then we plot a graph. So we will basically be plotting a graph of the boiling point, and this curve will be for boiling point. If we do the same for the melting point, we already have noted that even in the previous case, the zero value was not changing, so that does not change, but this actually varies with temperature. So this is what is called a phase diagram. We are going to come across this when we are looking at how the air conditioning system works, because this is very, very important. It is used even in the control of the air conditioning systems, because we are able to determine that if the refrigerant is at a particular temperature, what do we expect the boiling point of that substance to be at that particular pressure. So once we know what the boiling point is, remember we talked about the superheat and subcool. So once we know what the pressure of that substance is, let's say we are at 2 bars. At 2 bars, for instance, we know that our water should be boiling at around 120 degrees Celsius. So if our temperature reads 150 degrees Celsius, and that substance which is enclosed within the system is at 2 bars, then we know that we have superheated our substance by that 30 degrees, because from this phase diagram it shows that at 2 bars the boiling point is 120 degrees. So we have already boiled, and it is now in the gas phase, and we have superheated that substance by 30 degrees. That will be very important in the control of the air conditioning systems, and we will of course come across that when we get there. Now, I know you have heard me throw these two words here and there: Celsius, that is centigrade, and Fahrenheit, degrees centigrade and degrees Fahrenheit. Now this just is a plus, so that you may not be confused even when you are looking at the two figures. So here is a scale for the Celsius, and here is a scale for the Fahrenheit. We notice that on the Celsius scale, it is divided into 100 equal divisions, and each division equals 1 degree Celsius. Note that it starts from 0 degrees Celsius all the way to 100 degrees Celsius. Now, when we move to the Fahrenheit scale, the Fahrenheit scale starts at 32 degrees Fahrenheit, which is the temperature at which water melts in the Fahrenheit scale. Now, the Fahrenheit is divided into 180 equal parts. So note that for the Celsius scale, it's divided into 100 equal parts. For the Fahrenheit scale, it is divided into 180 equal parts. And we are talking about the same range. So it now runs from 32 degrees Fahrenheit to 212 degrees Fahrenheit. Now the question is, if I am reading in the Celsius scale and I want to convert to the Fahrenheit scale, what should you do? So we have already noted that in this case, the Fahrenheit scale is divided into 180 equal parts and the Celsius scale is divided into 100 equal parts. Therefore, the first thing we can note is that the Fahrenheit scale is 1.8 times larger than the Celsius scale. So to move from the Celsius scale to the Fahrenheit scale, we just first need to multiply by 1.8 and then add the offset value, which is 32 degrees Fahrenheit. So if we are at 100 degrees Celsius, so we multiply 100 by 1.8, which we are going to get 180 degrees Fahrenheit. Then we add the offset, which is 32, and we get 212 degrees Fahrenheit. Same case applies if we are at 0 degrees Celsius. We multiply 0 degrees Celsius by 1.8 and we get 0 still. Then we add the offset, which is 32 degrees Fahrenheit, and we get 32 degrees Fahrenheit. Now, when we are at Fahrenheit scale and we want to move to Celsius scale, we are already, even if we are at point B, we are already offset. So the first thing is to remove the offset, which we subtract 32 degrees Fahrenheit, then we divide by 1.8. So we still come back to this case. We have 32 degrees Fahrenheit. We want to convert to the Celsius scale. So we subtract 32 degrees Fahrenheit, which is our offset. Then we divide by 1.8, which still remains 0 degrees. Here we have 212 degrees Fahrenheit. We subtract 32 and we still get our 180 degrees Fahrenheit. Then 180 degrees Fahrenheit we divide by 1.8 and we get 100 degrees Celsius. Let's look at some examples. Celsius and Fahrenheit scale reading conversions examples here. We have 5 degrees Celsius and we want to convert to degrees Fahrenheit. So what we do is we take the 5, multiply by 1.8, then we add 32 and we get 41. Same case happens to this 10 degrees, multiply by 1.8 and add 32. 20 degrees, multiply by 1.8 and add 32, we get 64. Now, on the contrary, when we are in the Celsius scale, we are on the Fahrenheit scale, we have already noted that the first thing is to remove the offset because we are already offset. So we take our Fahrenheit value, which is 77, subtract the offset, then we divide by 1.8 and we get 25. Same case at 122 degrees Fahrenheit, remove the offset, then divide by 1.8 and we get to 50 degrees Celsius. We have already looked at this example where we were getting 212 degrees Fahrenheit. We subtract the offset, then divide by 1.8 and we get 100 degrees Celsius. So we have come to the end of this tutorial. Thank you very much. This is just a note of some of the references that we have used to be able to create this tutorial. Thank you.